the past several decades, the preparation of amorphous solid dispersions, or ASDs, to enhance the oral bioavailability of poorly water-soluble active pharmaceutical ingredients, or APIs, has become an increasingly more common approach. ASDs are made by the combination of an amorphous drug with an amorphous polymer, along with the addition of other excipients in an attempt to increase dissolution rate and extent, decrease nucleation and growth, and maintain supersaturation levels long enough to cause an appropriate pharmacological effect in the body. Supersaturation refers to having more drug molecules dissolved in solution compared to the crystalline solubility. An amorphous form of a drug has less structure between individual molecules compared to the crystalline form. This lowers the amount of energy needed to strip drug molecules from the matrix and dissolve in solution, and supersaturation can then be achieved. Crystal nucleation refers to the spontaneous conversion of amorphous drug to the crystalline drug in solution. These crystals can then grow, reducing the dissolution profile of the drug. The goal of this study is to evaluate the competing dissolution and crystallization mechanisms of an ASD with various levels of residual crystallinity. Dissolution experiments were conducted in two non-sink conditions of 50 milliliters and 100 milliliters, and one sink condition of 1000 milliliters. Only the non-sink condition of 100 milliliters was included here to simplify the results. Using a sink condition of 1000 milliliters allowed us to determine the crystalline solubility, and the two non-sink conditions allowed us to determine the amorphous solubility. The figure on the left highlights the dissolution profiles of 5 ASDs with varying amounts of crystalline content. The percentage of crystallinity in each ASD can be seen to the far right of each curve. The fully amorphous ASD, which is represented by the black dotted line, exhibited a dissolution profile reaching the amorphous solubility of 30 micrograms per milliliter. The fully crystalline ASD, represented by the gray dotted line, exhibited a dissolution profile reaching the crystalline solubility of 3 micrograms per milliliter. The figures on the right were taken with a polarized light microscope and illustrate the difference in rate of crystallization in an ASD with residual crystals, which is located on the bottom there, and a fully amorphous sample, which is located on the top. After 20 minutes of heating the crystal-free sample suspended in a small amount of pH 6.8 phosphate buffer, very few crystals had nucleated. However, after repeating this process with the sample containing residual crystals, much more matrix crystallization had occurred and very little amorphous material remained. This explains the decrease in dissolution achieved when increasing the percentage of crystals in an ASD, as seen to the graph on the left, going from 0% to 2% to 3% to 33% and then to 100%. By way of Raman spectroscopy, we examined the crystallization kinetics of two ASDs, one with 0% crystallinity and the other with less than 2% crystallinity. The graph on the left shows the crystallization kinetics of a purely amorphous ASD. After approximately 90 minutes, all of the amorphous drug had converted to polymorph form 2, which is metastable and has a higher solubility. The graph on the right shows the crystallization kinetics of a sample containing less than 2% crystals, which were primarily form 1. And even whenever a small amount of residual crystals remained in the sample, polymorph form 1 primarily grew in solution, and after about 50 minutes, almost all of the amorphous material had converted to form 1. This shows that residual crystals are form 1, and these crystals undergo rapid crystal growth, consuming amorphous material through a matrix route. However, when the ASD has no crystals, polymorph form 2 nucleates and grows in solution at a much slower rate compared to an ASD containing crystals. The residual crystals has proven to have a significant impact on the ability of bicalutamide to reach its maximum solubility in solution. This can be attributed to the rapid growth of residual crystals within an ASD matrix and was confirmed by PLM and PXRD analysis. Without crystallinity, the ASD can fully release and saturation. With increasing crystallinity, the maximum saturation, supersaturation achieved is reduced. The presence of a second polymorph increases the complexity of the crystallization kinetics in RASDs.